Previously, we studied first-order systems. Now we want to study graphical method to estimate gain and time constant of a first-order system. So we want to see, having the response of a first-order system, how can I write down the transfer function? Okay. Imagine you have this response. Okay, you have had a transfer function, you don't know what that is. That's what you're trying to do. You're trying to determine the transfer function of a first order system. All you know is that this is the response. What can you do? How can you find the first order system's transfer function? Again, remember that the final value of a first order system is its gain, or Kp, times the magnitude of the input, which we show with capital A in this course. But can I just say YSS here should be capital A times Kp? No, remember that is gonna be the final value of your response. Your response didn't start at 0, it had started at Y0. So if I have this response, your Kp times capital A, which is the magnitude of input, is not going to be YSS. What is it going to be? It's going to be YSS. Subtract from it Y0. How about your time constant? Time constant is the amount of time that takes for your response to get to 63% of its final value. So if this is the final value, I multiply it by 63%, and I find the point, which is T1, which I get to 63% of that final value. So that is going to be time constant. All right, so how do I determine these things? Well, as we talked about, gain is going to be YSS minus Y0 divided by your input's magnitude. So how big is your input? So if your input is this, your input jumps from U min to U max, so this is going to be your capital A, then capital A has caused this much jump in your output, right? So Kp would be YSS minus Y0 divided by U max minus U min. So that is how you determine the gain of the system. And then to find tau p, we write tau p is T1 minus T0, right? So this is going to be your time constant. Okay, let's see an example. For the first order system defined as T of S equals to 100 divided by S plus 100, find the time constant. So, well, you can't call this tau. Why? Because the system is not in standard format. What was standard format? Let me go back a few slides and see what standard format was. This was standard format. So in the denominator you have to have something times S plus 1. That's not what I had here, right? Something times S plus 1 is not the case here. So how can I make this something times S plus 1? Well, I have to multiply the numerator and the denominator by 1 over 100. So I'm going to have 1 over 100 times S plus 1 in the denominator, and then the numerator will just become 1. Now, this is Kp, or gain, and your tau p, or time constant, is just 1 over 100. Let's see another example. Sketch the response of the following system. This is a first order system because you have u, y, and then y dot, the first derivative of your output. The input's magnitude is 3. So if I take the Laplace transform and write it in standard format, I'm going to have 4 divided by s plus 2, right? So 4 divided by s plus 2, which in standard format is just 1 over 2s plus 1 in the denominator and then 2 in the numerator. And therefore, gain is 2, time constant is a half, is 1 over 2. And I can therefore sketch the response of the system as figure 6. So the time constant should be half, the gain should be 2. So if the input had the value of 3, because the gain is 2, your final value is going to be 6. It's going to be 3 times 2. And because the time constant is 2, it's half, if I wait 4 times that number, 4 times half, which is 2 seconds, I get to the final value. So this is the point that I'm assuming I'm at the final value. Okay, how about MATLAB? How can I utilize MATLAB for that? Well, first of all, we keep talking about poles and zeros of the system. MATLAB has a command called pzplot, pole zero plot, which, well, it plots poles and zeros for you. So we can use that. We can define a system, then use pzplot to plot poles and zeros. And then for plotting the step response, the command is just step. So I can define my system and then plot the step response by calling step on it. So let's say we have this system and we want to plot it. Well, I first define my system. If you remember, we have 2 ways to define a transfer function in MATLAB. We can say s equals to transfer function of s and then just type our system, or alternatively we can say g is tf of the coefficients of the numerator as an array and then coefficients of the denominator, so s squared plus 3s plus 2 as an array. Here I've used one of them, so I've used method 1, define my system g, and then pzplot g, and then pzplot g, and then step g. So it's gonna just plot for me the step response, and it's gonna also show me the pole zero location or the plot for poles and zeros. Okay, let's see another example. Consider a first order system g, and this is the output shown in this figure to a step which starts at 1, and as we can see, and so the input jumps from 1 to 4. What does it mean that step jumps from 1 to 4? It means that the magnitude of the input is 3. So I have an input with magnitude of 3, and this is the output. Find the transfer function of the system. Well, the input's magnitude is 3, and as you see, the output has jumped from 1 to 5. So 4 here. What is the gain? Is 4 divided by 3 or 1.33. Now, again, if I want to find 63% of 63% of final value, I shouldn't multiply 63% with 5. That's going to give me the wrong number. I don't want to find 63% of 5. I want to find 63% of the jump here. So 63% of 4, and then subtract that. So I'm going to end up being at 3.52. So I add 1 with 63% of 4 to give me 3.52, and that would be the time response. So the time that I get there, so here, this is going to be time constant, which is 1. So the transfer function ends up being 1.33 divided by s plus 1. And that's the end of first order systems.